I am Kishore Jethanandani, the Chief Futurist at Futuristlens, an industry analyst and content strategy and content generation consulting company focusing on future-proof enterprise business technology solutions and innovation. Hello, good afternoon, or good evening, depending on where you are in the world. I am so glad you joined this event organized to discuss enterprise innovation. Just so you know, I have used AI tools to augment my human voice for clarity, ease of communication, and ease of comprehension. I encourage you to comment, ask questions, contribute facts, and share experiences to make the best of this event. I reviewed each of your LinkedIn profiles. I noticed that many of you have some involvement with enterprise innovation as network operators, device suppliers, or business solutions providers. I would respond to each of you after the presentation. I will start by clarifying the meaning and characteristics of enterprise system innovation. System innovation goes beyond upgrades of silos. It spans multiple stages of value creation and incorporates several business units and technologies to create a cohesive and evolving business solution. Enterprise innovation is a relatively recent phenomenon dating back to 2019 when the U.S. government pursued a policy of shared radio spectrum that included allocations to private companies. Incidentally, a recording will be available if you want to review the content at your leisure. Due to time limits and technology risks, I cannot respond instantly, but I will be in touch. Additionally, I have linked the Calendly app, so you can book an appointment to discuss any specific matter you might want to discuss or pursue. The enterprise was allocated the most coveted slices of the mid-band CBRS, Citizen Band Radio Service, radio spectrum, with frequencies in the range of 3.5 GHz to 3.7 GHz. These frequencies are best suited for developing business solutions. Enterprises can implement high bandwidth applications with these frequencies. They can also provide solutions to a large cluster of customers spread over an expansive geographical area, such as a metropolis. The shared spectrum policy allowed private companies to own and control their radio spectrum, separate from their connections with public telecom companies. They could design their software-defined networks and develop network-based business applications and system solutions. Software-defined systems subsume interrelated enterprise applications and execute consecutive activities automatically for a continuous workflow, considerably saving human effort. For example, an application operating a robot to complete a manufacturing process in an automobile factory is a step in a work in progress followed by transporting semi-finished goods with an automated guided vehicle, a GV, to another station for the following process. A typical application in the early days was flexible automation in automobile plants. Until then, automobile plants could only automate large plants with standardized production. Software flexibility allowed robots to be programmed for small lots in a market where customers crave a variety of automobile models. The enterprise could implement flexible automation because it could use a dedicated spectrum for the remote control of robots and AGVs, and it could control the traffic on private networks for reliability. Software-defined systems subsume interrelated enterprise applications and execute consecutive activities automatically for a continuous workflow. For example, an application operating a robot to complete a manufacturing process in an automobile factory is a step in a work in progress, followed by transporting semi-finished goods with an automated guided vehicle, a GV, to another station for the following process. Software makes flexible automation possible as robots can be reprogrammed to manufacture a variety of lot sizes in a market where customers crave a diversity of automobile models. Until recently, automobile plants could only automate large plants with standardized production to realize economies of scale. High-bandwidth private networks dedicated to individual enterprises allow the remote programming of robots and navigation of AGVs. They can maintain a consistent service quality by controlling the traffic volume in the network. Enterprise innovation is an evolving phenomenon. The first private networks supported software-defined enterprise systems spanning the individual units of companies, such as a factory. They expanded the coverage to adjacent compounds or yards to increase productivity. Further productivity gains are realized by including partners delivering components or assemblies. Some can also decide to include warehouses and transportation centers. A single private network or a group of interconnected networks serves and controls their interlinked processes. Together, they increase the productivity and predictability of the operations. Today's event will focus on second-generation software-defined systems that have taken shape over the last 2 years. These leverage AI for data processing, the Internet of Things, IoT, for data capture, and display technologies, wearables, and digital twins for situational awareness and decision-making. They have become the pillars of enterprise system innovation. IoT sensors data makes valuable data visible, otherwise elusive to human vision and senses. For example, building cracks are invisible to humans and can cause energy losses. However, sensors detect leaking vapors. Building managers will likely embed sensors in their buildings to prevent losses, only to gather masses of data that are not actionable without related data on the time, location, and the density of leaks. AI sifts the data to uncover nuggets and pinpoint the root causes of problems. Virtual displays of the buildings and leak points help direct mechanics in conducting repairs to stem energy losses. Pervasive networking, aided by low-orbit satellites and mesh networks, helps gather data from remote corners and locations that traditional networks cannot reach. Today, low-orbit satellites cover almost all corners of the world. Mesh networks can insert nodes in any asset, such as a truck, and receive signals from anywhere. 3D visualization clarifies decision choices. The dramatic rise of drones and drone swarms in the military. Digital guerrilla warfare has risen from the ruins of the conventional army shattered by drones and drone swarms pioneered by unsuspected non-state actors like the Houthis. They lay to waste expensive weaponry like tanks and armored vehicles. The modus operandi of the modern adversaries is asymmetric warfare with stealth mode operations, speed and surprise in execution, and precision in targeting. Some adversaries have other types of arsenal, including hypersonic missiles that are elusive to radars and miniature submarines with a muted acoustic signature that operate in cluttered coastal waters to hide. The reinvention of the military is inescapable. The new architecture sees information as the key to future warfare. Wars generate enormous volumes of data spread throughout the battlefield. Aggregating the data provides situational awareness. Greater use of AI powers autonomous weapons. AI selects targets from battlefield data for precise attacks. It does not miss lurking threats because of omnipresent surveillance with sensors and computer vision. Drones are remotely maneuverable, and drone swarms are also remotely configurable. Rapid reconfigurations of drone swarm formations will power guerrilla-like attacks on adversaries operating as small or large groups. The formations can also conduct complementary operations such as rescue, offense, and defense by each unit communicating with each other. They adapt their strategy and tactics to the threats they encounter in the moment. Their speed of operations can vary depending on the urgency of the task. Conventional weaponry like fighter jets remains valuable for humans' role in executing the strategy and tactics for drone swarms. Human intelligence guides autonomous weapons for unforeseen situations. They can also find enemies hidden indoors or underground. Most operations need little or no military training. Autonomous weapons defense is timely. They fire when data feeds from the IoT and AI flag threats. Today's IoT platforms, like Lattice, fuse data from third-party sensors to gain holistic situational awareness. Hidden in enclosures until they take off on missions, the linked video has a live demo of how they operate. The risk of damage of autonomous weapons is low because of their invisibility, which makes them reusable. Hypersonic missiles can be intercepted only by small autonomous satellite swarms. They target hypersonic missiles in the boost phase when their flight path is predictable and their plumes reveal their flight path. The satellites share information and leverage AI to coordinate their actions. Traditional methods of small submarine detection with acoustic signals are unworkable with ambient noise in shallow waters clutter aggravated by noisy unmanned submarine swarms. More sensitive quantum sensors and reading of disturbances in magnetic fields filter out noise. Military force is greater than the sum of its wings with collaborative combat. In today's battlefield, collaboration is with manned and unmanned forces. The shared information from the Internet of Things helps plan joint actions. Communication with software-defined networks, including satellites and mesh networks, helps coordinate missions by dispersed forces. They can strategize on combat options based on the intelligence extracted from artificial intelligence. Soon, each soldier will have a 3D view of the battlefield in their field of view and complement their peers for force multiplication. The theaters of war, such as the South China, will concentrate naval forces. In an age of stealth mode warfare, unseen threats could be hypersonic missiles fired from a remote location. It can't be detected or counted without Space Force. The surveillance of adversary movement will take unmanned drones. Stealth mode attacks by Marines could lead to the seizure of an island naval base. Military force is greater than the sum of its wings with collaborative combat. In today's battlefield, collaboration is with manned and unmanned forces. The shared information from the Internet of Things helps plan joint actions. Communication with software-defined networks, including satellites and mesh networks, helps coordinate missions by dispersed forces. They can strategize on combat options based on the intelligence extracted from artificial intelligence. Soon, each soldier will have a 3D view of the battlefield in their field of view and complement their peers for force multiplication. The theaters of war, such as the South China, will concentrate naval forces. In an age of stealth mode warfare, unseen threats could be hypersonic missiles fired from a remote location. It can't be detected or counted without Space Force. The surveillance of adversary movement will take unmanned drones. Stealth mode attacks by Marines could lead to the seizure of an island naval base. Data-driven technologies have fundamentally transformed supply chains after the shock of chronic disruptions during COVID-19. Matching demand and supply was tenuous during the crisis. A high concentration of supply from China proved to be a catastrophic vulnerability during unanticipated shutdowns when supplies plummeted. Demand varied wildly as the pandemic created a massive demand for medical products, frozen food, and sanitation goods. The availability of transportation was uncertain as workers were affected by health mandates and work-from-home policies. No one means of transportation could meet all needs. Segmentation of markets with a growing number of customized products and distribution channels added to the uncertainty of forecasting and fulfilling demand. Spot rates for shipping and inventory to sales ratios fluctuated. The expected time of arrival was a variable target. Tracking the flow of goods has become a part of supply chain standard operating practices. It starts with becoming aware of raw material losses that could affect production. It provides data on the replenishment of parts and raw materials and automates reordering to keep production flowing. IoT can monitor conditions such as temperature, pressure, and humidity to understand the root causes of disruptions and make automatic adjustments to prevent them. Tracking the location of packages helps estimate the expected time of arrival. A deeper analysis would reveal the causes of delays, such as shortages of chips that affected automobile production during the COVID crisis. Supply chains changed their architecture and moved from 3PL logistics to 4PL management. The distinct function of 4PL is to manage the supply chain end to end to optimize its operations. It exercises central control over all its decentralized operations, including transportation, warehousing, and order fulfillment. It aggregates data from every layer of the supply chain to gain situational awareness of supply chain operations. It complements the physical operations of 3PL with a digital layer. 4PL supply chains emerged to manage the complexity of modern day supply chains with conflicting demands on speed of delivery, reliability, risk exposure, and cost control from an expanded choice in the sources of supply. They aid supply chains in adapting to unexpected events in modern supply chains. They leverage AI and digital twins to optimize supply chains. Risk mitigation by supply chains elevates the complexity in their management. Supply chains have diversified their sources to include local, regional, and global sources in response to higher frequencies of disruptions. Global centers are presumed to have the lowest costs, but are most affected by disruptions and are prone to time delays or uncertain ADAs. Local supplies have the shortest lag time for delivery, but are likely to be the higher cost sources, and regional are in the middle of the spectrum. Risk mitigation by supply chains elevates the complexity in their management. Supply chains have diversified their sources to include local, regional, and global sources in response to higher frequencies of disruptions. Global centers are presumed to have the lowest costs, but are most affected by disruptions and are prone to time delays or uncertain ADAs. Local supplies have the shortest lag time for delivery, but are likely to be the higher cost sources, and regional are in the middle of the spectrum. Similarly, the fastest means of transportation, by air, costs far more than ocean transportation, which costs the least but is the slowest. Predictable demand for the season can be fulfilled with the expectation that the inventory will be sold. Suppliers prefer lower transportation costs for such deliveries. Unpredictable demand likely comes close to the beginning or later in the season. Supplies are rushed by air transportation, particularly when prices rise due to higher demand. For unpredictable demand, suppliers need Uber-like flexible sources of vehicles at varying, market-determined prices. 4PL supply chain managers have created an infrastructure of data stores and AI to evaluate their options. Mixed reality wearable glasses render AI-generated intelligence actionable by displaying it in users' field of view. Unlike handheld smartphones, wearables don't detract attention from the missions users want to accomplish. Instead, they focus users' attention with immersive and interactive experiences, context-specific visuals, and data. Execution entails minimal friction as commands are executed with natural user interface controls such as eye movements or voice commands. Commercially viable products have lagged due to the formidable challenges of designing and manufacturing wearables. A second generation of wearables technologies has brightened their prospects by making them lighter, shrinking their size, and vastly improving display quality with holographic visuals. The prospects of commercial breakthroughs for their market growth are more promising than ever before. Wearables use cases have exploded as AI applications and solutions boom. The players in the AI industry have invested large sums of money into wearables thus far with modest success. Mixed reality makes the workforce more productive. Digitized documentation, such as manuals, is overlaid into real-world operations, such as aircraft maintenance, to complete tasks faster. Workers can be effective by closing the knowledge gaps in their knowledge by updating it or by receiving virtual directions without necessarily spending time training. Remote collaboration with experts makes it feasible to troubleshoot complex equipment without transporting them to a site at great expense. Mixed reality shortens the time between conceptually designing and implementing a product in real life. By virtually observing how well initial concepts fit real situations and meet customer needs, mixed reality shortens the time between market research, product design, its iterations, and product market fit. An interior designer, for example, can observe virtual furniture and fixtures in an actual building before their fabrication, purchase, and deployment, saving considerable time and cost for customers and designers. Business strategy is taking shape in parallel with technology megatrends. The military has dropped its fixed price contracts to encourage the entry of startups and spur innovation. These startups have pioneered autonomous, data-driven hardware and software technologies. They take the risk of investing in the R&D of a new arsenal and are rewarded with variable margins. End-to-end supply chains are focused on achieving a predetermined expected time of arrival. They have created a platform to build applications for risk mitigation, process improvement, and optimization to remove bottlenecks and speed breakers. The mixed reality wearables industry is adopting waveguides to shrink the device's size, implement micro-optics to reduce their weight, and adopt holographics to improve image quality. How will these technologies and megatrends shape the future? As stealth mode operations expand, the military will focus on increasing precision in targeting and closing gaps, especially in targeting submarines. It will integrate space, ground, and underwater data to expand situational awareness and precision targeting. We can expect advances in quantum sensors, innovation in AI signatures to filter noise, and building technologies for sensing with alternative means other than acoustics. Tracking elusive arsenal like hypersonics will take precedence. Small satellite drone swarms will grow as their costs decline. Supply chains will gather microscopic data on goods flow by tracking at the individual asset and package levels. This will sharpen predictive expertise as more variables are incorporated into forecasting models. Digital twins will simulate an expanded range of scenarios to consider and stimulate innovations in strategy and tactics to mitigate risk. A hiatus between the expected outcomes and the actual numbers will uncover more process and technology improvement opportunities. Multimodal AI, including object identification, charts, and graphs, will increase the applications of mixed reality wearables. More computing capabilities with wearables will open the way for interactive applications. The size and weight of wearables will decline with the adoption of micro-optics. Holographic glasses will expand data visualization applications.